Hello everyone and welcome back to Techmine Guru. I'm your coach Supratim. Today we are going to tackle a topic that haunts many developers. By the end of this video, it is going to be your absolute superpower. In DSA lecture 20, we are going to dive deep into interview problems on recursion. We will conquer this by breaking it down into the 4 domains of recursion. First, math dynamics, where we will explore the power function a to the power n and learn how to optimize our code to go from O of n to O of log n time. Second, array basics, focusing on printing and summing using both forward and backward passes. Third, advanced arrays, where we will tackle the index finder by carrying memory down to the base case. And finally, string traversal, looking at palindromes using the 2-pointer pincer technique. Let's jump right into problem 1, finding a to the power n the naive way. Our goal is simple. Given an integer a and n, find a power n. We are working within the constant of a 64-bit integer where n is lesser than equal to 10 to the power 8. So to solve this, we have written a simple code int power of a comma n, and this is our base case. Since for every recursion we need one base case, right? Because every base on the power 0 will return 1 as the result. So this will be our base case where n is equal to 0, return 1, or else return power of a comma n minus 1 into a. So if we use a basic approach, looking at a call stack that goes from 5 power 3 to 5 power 2, 5 power 2 to 5 power 1, 5 power 1 to 5 power 0. Our time and space complexity both will be O of n, right? But can we do better? Absolutely. We can use fast exponential to make O of log n leap. So let's see how. So the key observation here is that a to the power 10 can be expressed as a to the power 5 into a to the power 5, meaning we can completely half our work. So if n is even, a to the power n can be expressed as a to the power n by 2 into a to the power n by 2. So if bases are same, the powers will add up. So n by 2 plus n by 2 will give you the result as n, right? What if n is odd? In that case, a to the power n can be expressed as a to the power n by 2 into a to the power n by 2 into a. So there will be one extra a in case of odd. So if you visualize this tree, power of 2 comma 5, in the next call, it will be power of 2 comma 2, right? So this power of 2 comma 2 with this power of 2 comma 2 can give back this result again. But in this, if n mod 2 is equal to 0, we will return p into p, and else we will return p into a. So every time we have to recursively call the half of it. And our base case here will be again the same, which we have seen earlier. If n is equal to 0, return 1. So power of 2 comma 5 will call power of 2 comma 2. Power of 2 comma 2 will call power of 2 comma 1, and power of 2 comma 1 will call power of 2 comma 0. So this will give the result as 1. As soon as this will give the result to this will also give the result to power of 2 comma 2, and this will give the result of this. So to optimize it better, we have taken power of a comma n by 2 as p, and in the next step we are simply checking if n is even or odd. If n is even, then we just need to do return p into p, else we will return p into the base itself. So by visualizing this tree, you will see the total level drops to O of log n, right? Previously it was O of n, now it dropped from O of log n, that is from 5 to 2, 2 to 1, and 1 to 0. So this will reduce our total calls and will bring both our time complexity and space complexity down to O of log n, right? So this is a lead code problem. The link I have mentioned in the description as well. Now moving on to problem 2, recursive array traversal. Our goal is to print all elements in an array recursively. So in this, if you see the code, our base case is when our index will reach the size of the array, we will return from it, or else we will print the array and we will call the print array function with index plus 1. So suppose this is the array 1, 2, 3, 4, 5. So first a comma 0 will get called. It will check whether this 0 is equal to a of size or not. A of size will be 5, right? So it will print a of 0, which will be 1, and it will call again print array with a comma 1. Then again inside that 1 will be checked with size. This function block will not work. Again it will print 2. It will call the same function a comma index plus 1 with a comma 2. Again it will check whether 2 is equal to 5 or not. It will return false. It will print 3, and it will again call recursively a comma 3. Similarly, it will call for 4 also, and when the index will reach at 5, it will see 5 is equal to 5, so it will come out from the array. So once it comes out from the array at a comma 5, our control will come to a comma 4, then our control will come to a comma 3, then our control will come to a comma 2, and then our control will come to a comma 1. So everything was getting called from the last block. So this will return to the main function, and our code will print all elements recursively. So what is the time complexity and the space complexity? So time complexity will be O of n, because inside this function block, the time complexity is O of 1 into number of function calls will be 5, right? So it will be O of n. And similarly, since we are not taking any extra space inside the function, so it will be O of 1, but in the total, we have taken an array. So that's why our space complexity will be O of n. Next will be the array sum. We have to do the sum of the array recursively. So if you closely observe, this calculation will happen strictly during the unwinding phase on the backward pass. The function goes deep until it hits the base case and returns 0 and calculates the sum as it unwinds back up the stack, right? So let's see how. So let's suppose we have an array of 1, 2, 3, right? So this find sum will call find sum of a, 0. It will check whether this 0 is equal to a dot size or not. The size of the array will be 3, right? This block will not work. Now it will return a of index, which will be 1 in our case, plus it will recursively call a, 1, right? So when it will recursively call a, 1, it will also check whether in 1 is equal to size of the array or not. It will return false. So a of 1 is 2, right? So it will call 2 plus a of 2. Now a of 2 will call find sum of a, 3, right? It will check whether 3 is equal to 3 or not. It will return, right? It will return 0. But when it will return 0, at that time, our a of 2 will be added, right? Here we have 1 plus a of 0. Here we have 2 plus a of 1. And here we have a of 2 plus 0. So what is the a of 2? A of 2 will be 3. So this function will return 3 to find sum of a, 2. So in find sum a, 2, it has a of 1 plus find sum of a, 2. Find sum of a, 2 is given as result 3 and a of 1 is 2. So 2 plus 3 will be 5. Similarly, find sum of a, 1 will give the result as 5 and 1 plus a of 0 will give the result as 1 plus 5, which is equal to 6. So if you have observed in this, the function goes deep until it hits the base case and it will return 0 and calculate the sum, and it is calculating the sum as it unwinds back up to the stack. Now problem number 4. So here our goal is to find all indices where element is equal to b, and you have to print the index of those elements in a new array. So since we will have a new array for this, we are obviously knowing that the space complexity will be O of n only. So for example, a is 1, 2, 3, 1, 1, and our target element b is 1. So what will be the resultant array? 0, 3, and 4th index, right? So the key insight here is to observe how we can pass the state. So for that, we will keep a variable cnt count, which will count down throughout the calls. And finally, when we will hit our base case at the end of the array, the count will tell us the exact size needed for our answer array. So at that time, we can instantiate it by returning new int of count and fill it as we unwind. So let's see how we can do this. So let's see the dry run for the same using this code as well as this dry run. So when index will be at 0, suppose we are calling with a array, b target element, and we are starting with the 0th index and our count is 0, right? So at the index 0, our value will be a of 0 is 1, which is equal to the target element 1. So our count will become 1 here. So here in the answer array, we will have a of count, which is 0, because we started from a, b, 0, 0. So a of 0 will be equal to index, and index is also 0. So this is stored, right? But before storing, we will call again this find function with a, b, index plus 1 and count plus 1. So here after this, it will call a, b, 1, count as 1. So at the index 1, you will see there is no match. So our count will remain the same. So in this find where a, b, 1, 1 will come, our this if block will not work. At that time, we will again call find function a, b with index plus 1 and count we will not increase since our element didn't match the target element. After that, we will call index 2. Index 2 will again not match. So that will also come as no, and this block will be executed in that case again. So it will be a, b, 2, 1 only. Again, when this find function will call, it will again check whether the index is equal to a of size or not. If not, it will check if index is equal to target element or not. Since we came to a of 3 now, because this will call a comma b comma 3 comma 1, right? So at that time, 3, the element present in the 3 will be equal to our target element. So we will, in this case, we will increase both our count as well as index. So our index will become 4 and our count will become 2, right? Now again, this block will execute and it will call for the final check, find of a comma b with index as 5 and count as 3. So we will check here that index has reached our size, which is our base case. We will instantiate here an array with the length of the count. So what is the length of the count? It will be 3. So as soon as it will come out, it will store the index. Answer of 2 will be equal to 4 because 4 is our index. Similarly, once this is over, this 4 comma 2, the control will come to a b comma 3 comma 1, where it will check again that where it will keep answer of 1 is equal to 3. Now the control will come to a comma b comma 2 comma 1, which is from here. Here it will not keep anything. It will just come back to a comma b comma 1 comma 1, and this will again will not keep anything. It will again come back to a comma b comma 0 comma 0, where it will come in this if block and it will store answer of 0 as 1. So when we finally hit the base case at the end of the array, count will tell us the exact size needed for our answer array. So here the time and space complexity will be O of n only, right? Because inside this function, this is O of 1 only, right? And we are calling n times function, so it will be O of 1 into n, which will be O of n. So let's move to our last problem of day to day. So our goal is to check if a string is palindrome or not using 2 pointers and recursive technique. So in this, our recurrence relation will be s of I is equal to s of j. And for working like a 2 pointer, we will move the I pointer towards the right side and we will move the j pointer towards the left side. So that we called this is palin function with I plus 1 comma j minus 1. And our base case will be whenever I will cross j, we will return true. So our code logic is this much only. Whenever our I pointer will cross the j, we will return true so that we can come out our recursive relation. And if at any time s is not equal to s of j, we will return it as false because this will tell that this is not a palindromic number. So let's see with 2 examples. One which is a palindrome and one which is not a palindrome. If palindrome will be called with 0, 4. So 0 is greater than equal to 4. It will return false. This condition will not work. It will check whether 0th and 4th element are equal or not. It will say yes, and then it will return 1, 3, right? So I pointer will move 1 place here and the j pointer will move 1 place here. So it will again go here. It will check 1 is greater than equal to 3 or not. This condition will not work, and the element in 1 and 3 is same. So this condition will also not work, and this will again move the pointer. So I will be equal to I plus 1 and j will be equal to j minus 1. So I will be 2 and j will be 2. Now when this is palin will get called, it will check this condition. If 2 is greater than equal to 2, it will return true. Once it will return true, it will reach here because this was also called from the last, it will also return true. And since this was also called from last line of the function, it will also return true. And finally, in our main, it will return true. Similarly, if we do for a non-palindromic number, so is palin will call 0, 4, where 0th and 4th element will be equal. It will call 1, 3. Now 1, 3 will see that first element is A and third element is C. So this will return false. As soon as this will return false, this function will also return false and it will return false to the main function. So again, the time complexity here will be O of n and the space complexity is O of n. So to wrap things up, I want you to remember the recursion playbook. Every solid recursive function needs a base case, a recursive leap, and a state management. Let's do a quick recap of the techniques and complexities we learned today. For the power of a to the power n problem, we used fast exponential, which gave a complexity of O of log n. Then for arrays and sums, we used the bubble up logic, which again gave us the time complexity as O of n. For finding indices, we used state passing logic with our count variable, which gave us again O of n time complexity. And finally, for the palindrome, we used 2 pointer collapse technique, which also resulted in O of n only. So that's it for today's deep dive. In our next class, we will be tackling modular arithmetic, and GCD problems. If you found this demystifying helpful, make sure to like, subscribe to Techmine Guru. Till we meet again, keep coding, keep optimizing, and keep learning.